Okay. It is Monday, March 19th, and I might have to take some phone calls due to inclement weather, causing all sorts of headaches for me, picking up kids from school early and trying to teach class. But we'll see what happens. So in the meantime, I apologize in advance if I have to stop the video to get the phone, but we'll figure things out. All right, so couple of things. I'm going to try to rush through homework 5 because somebody else wants to use the team room, and I wish you didn't, but I'm trying to be accommodating and share. So, all right, homework 5. ODE for the standard mass spring damper system for parameters. Mass is equal to 1 kilogram. Stiffness is 100 newtons. Let me just write this cut down. M is equal to 1 kilogram. Stiffness is equal to 100 newtons per meter, and damping is equal to 25 newton seconds per meter, otherwise known as a newton per meter per second. Use Laplace transforms, that's the key part, to obtain the free response to, let's see, x naught is equal to 0.1 meters, and v naught is equal to 2 meters per second. All right, so to do this problem, recognize that you start off with the differential equation x double dot plus d over m x dot plus a over m x is equal to 1 over m f of t. And for our particular situation right now, f of t is equal to 0. We take the Laplace of both sides, and of course we get s squared x of s minus s x of 0 minus v of 0. That's the Laplace of x double dot plus b over m times the Laplace of x dot, which is s x of s minus x of 0. And then we have plus k over m x of s is all equal to 0, because the Laplace of 0 is, what do you know, 0. What a big surprise. This isn't going to change for problems 1 and 2 and 3 and 4. So what I'm going to do, goofy though this may be, is I'm going to solve problem 1a, 2a, 3a, 4a, and then we'll move on and try to do things in that fashion. The initial conditions are all the same, actually, on all 4 problems, so we'll go from there. So this is 1a for now. Now we're going to change it up to 2a. The point here is this. We're going to group terms and solve for x of s. Well, you have s squared plus b over m s, let's do that again, s plus k over m times x of s plus, what do we have? Let's see, we have b over m, nope, wrong one, minus sx naught, and then it's going to be minus b over mx naught, so it's going to be minus s plus b over m x of 0 minus v naught is all equal to 0. In other words, solving for x of s is actually equal to v of 0 plus s plus v over m x of 0, all divided by s squared plus b over m s plus k over m. So what we're going to do is actually evaluate this for our given v naught, x naught, b, m, and k. There's a b and m again over there. That'll give us x of s. Then we do the inverse Laplace transform of that, and we get the answer. So let's go ahead and do that. First things first, some investigation into the nature of the solution is appropriate. S squared plus b over ms plus k over m looks an awful lot like the characteristic equation, because it is, except that it's a Laplace transform denominator. It's actually the denominator as part of the transfer function as well. The numerator of the transfer function would simply be 1 over m, but we're not using the transfer function because the input is 0. Anyways, I know I'm tossing out a lot of little factoids and things like that, but I do expect you're going to be able to pick up on that as you go along, since we've covered this extensively in class. So, yes, special case, n is equal to 1. Second two problems, I think, n is equal to 2, just to be different. Anyways, let's go ahead and take a look at the nature of the response being 1, 2, and 100, like that. So let's see. S squared plus, actually that's not 2, that's 25, sorry. S squared plus 25 S plus 100. Now you'll notice this is just S squared. This is B over M. M happens to be 1. This is K over M. M happens to be 1. Okay, now let's just go ahead and solve this equal to 0. What do we get? Well, as it turns out, 100 is, when we factor it out, what do we get? 100 times 1, we get 2 times 50, we get 4 times 25, we also get 5 times 20. What do you know? We have S plus 5 times S plus 20. And this is what I'm trying to distinguish my little s's with a little, whatever you want to call that, the zigzags on top versus the 5 are just like that. So we get S squared, 5S plus 20S makes 25S, and 100 like that is equal to 0. So what that tells us is that the nature of the response ultimately is going to be x of t is equal to, let's just call it A, e to the minus 5t plus b hat e to the minus 20t, b hat as opposed to b. That's what this denominator over here actually tells us when we sub in those numbers. So what we're really solving for, if we solve this out using our initial conditions, is that x of s is equal to, let's see, we have v of 0 was 2 plus, this is going to be s plus, and initial condition 0.1 for the position, be s plus 25 times 0.1 all over s plus 5 times s plus 20. We can actually kind of group terms. We have 0.1 s plus, let's see, we have 2 plus 25 times 0.1 is going to be 2.5, so that's going to be plus 4.5 all over. Instead of doing the s squared, we'll do this as s plus 5 times s plus 20. And so what we're saying is, all right, 0.1 s plus 4.5 all over s plus 5 times s plus 20 is equal to a over s plus 5 plus b hat over s plus 20, like that. How do we know that? Because we know that with these two factors, the s plus 5 and s plus 20, we can do partial fraction expansion of that form. So, to solve this out, what we can do is to solve for a, is we multiply both sides by s plus 5. S plus 5 over s plus 5, that'll go away. S plus 5 over s plus 20 will be the coefficient times b hat. We'll have s plus 5 over s plus 5 going away. We'll end up with an s plus 20 over there. So if we did, let's just do it like this. Mult both sides by s plus 5. As I say in class, that smudge is an s. Okay, s plus 5. Okay, to do that, what we'll end up with is 0.1 s plus 4.5 over s plus 20 is equal to a plus b hat times s plus 5 over s plus 20, comma, let s be equal to minus 5. This has to hold for any possible value of s. If s goes to negative 5, this term goes to 0. Okay, and so what we have then is that a is equal to 0.1 s plus 4.5 over s plus 20, evaluated at s is equal to minus 5. 0.1 times minus 5 is going to give us minus 0.5 plus 4.5 is equal to 4 over minus 5 plus 20 is going to be 4/15. All right. Same thing for b hat. Okay. Then mult both by s plus 20 up here, and let s be equal to minus 20. If you do that, you have 0.1 s plus 4.5 over s plus 5 is equal to, the a term is going to go to 0, because when we multiply by s plus 20 and we let s go to negative 20, then it goes away. This is going to be equal to b hat, and this is all at s is equal to minus 20. All right, so b hat is equal to 0.1 times minus 20 gives us minus 2. Minus 2 plus 4.5 gives us 2.5 over minus 20 plus 5 is going to be minus 15. 2.5 is going to go into 15 what? 1, 2, 3, 4, 5, 6 times. So minus 1/6. So if I get it right, and you never know, I might have done it wrong, x of t is actually equal to 4/15 e to the minus 5t minus 1/6 e to the minus 20t. And let's check. But I got it right. There's always some question as to, okay, did I screw up and make an algebra error? So that is 1a. Okay, that's how you do it. I got a transfer function that I'll go through. I'm not going to do that right now. We'll come back and do that in a minute. Let's do the next problem. Given 2a. All right, 2a, m is equal to 1, k is still equal to 100, and b is equal to, oh, what do you know? We're going to have less damping now. What a shock and surprise. All right, so does anything else change over here? No, absolutely not. Although I would like some extra room, and so what I'm going to do is erase some of this stuff, and assume you can hit pause, scratch it out yourself, however you want to do it. But let's go ahead and do this, because now we're going to do completing the square. How do I know that? Well, I know that because I wrote the problem, but also that's just the way that it works. As I try to give you something that's underdamped, I try to give you something that's overdamped. So x of s for the free response is going to be equal to what we said down here. V is 0 plus s plus v over m x of 0 all over s squared plus v over m s plus k over m. Now, if you memorize that, you can do it. I think you're wasting your time. Figure out how we got there. It only takes you like 30 seconds, if that much time to actually get this, if you work it out yourself. If you know what you're doing, you don't have any need to memorize or very much. A little bit, yes, but not a lot. So let's take a look at the denominator here. What do we have? We have s squared plus 12 over 1 gives us 12. That would be times s plus 100 is equal to 0. Therefore, s is equal to, oh, right. Hang on a second. Hi there. Hang on just a second. Let me hit pause. Okay, coming back again. All right, so if you try to factor this in your head, it's not going to work. There is no factor of 1 times 100. Okay, that gives you, 101. 2 times 50 gives you 52. 4 times 25 is 29. 5 times 20 is going to give you 25 here. That's about where we come out to, right? 2.5 times 40 gives you 42.5, whatever. We can work out the numbers. Let's go ahead and use the quadratic formula on this. So you have minus b, this is, of course, s squared, little a s squared plus little b s plus c is equal to 0, and we're solving out for s. So it's little b minus b plus or minus the square root of little b squared, which is going to be 144 minus 4ac, 4 times 100, so that's minus 400, all over 2 times a, and a happens to be 1. All right, so 144 minus 400 is going to give us 256. So this is equal to minus 6, minus 12 over 2 is minus 6, plus or minus, let's bring the 2 inside the radical, so we'll have 256 divided by 4, because when the 2 goes in, of course, it gets squared, okay? 256 divided by 4, and by the way, that's negative, that's the key answer there, so obviously it's going to be a complex number for the roots. 256 over 4 is going to be 64, right, because 4 times 60 is 240 plus another 16, so this is going to be minus 6 plus or minus j square root of 64, otherwise known as minus 6 plus or minus 8j. So A couple interesting things will happen, and we'll utilize this result again in a few moments. What you'll find is, let's see, how should we go about doing this? We got to complete the square. How about we do that? So we know that this then is going to be s plus little a, different little a, okay, not the same little a here, so get rid of this. S plus a squared plus omega squared is equal to s squared plus 2as plus a squared plus omega squared, like that, okay? Is equal to, let's not do it like this, let's just say this is actually equal to, okay, s squared plus 12s plus 100, all right? So obviously a is equal to 6, and then a squared plus omega squared is equal to 100, so omega squared is equal to 100 minus 36 is equal to 64, therefore omega is equal to 8. So what we're doing is we're saying, look, x of s, then, for this particular problem, I've gone and done some numerical manipulation here. I suppose we can write it down here. X of s is going to be equal to, the numerator doesn't change any as far as the form there. V of 0 being 2, b over m being 12 times 0.1. Let's just write it as this. V of 0, heck. X of s is equal to, yeah, let's do it. V of 0 plus s plus b over m, x of 0, all divided by, now we have s plus 6 squared plus omega squared. That tells us that at least my form x of t is going to be a damped sinusoid, a damped harmonic function. And so we could say it's actually equal to, let's do it this way, is equal to e to the minus 6t times a sine of omega t plus b hat cosine of omega t. Laplace transforms are all about, we solve out for x of s, we look at the denominator, and then we conjecture from that what our answer is going to be. We cast our Laplace transform into a form that we can algebraically solve for this a and the b. Where does the minus 6 come from? Where is the, and actually omega, I shouldn't say that, this is, let's see, we'll do this again, plus 8 squared, that'll be 8t plus b hat cosine of 8t, like that, right? The 8 gives me the frequency, the 6 gives me the damping rate, if you will, the exponential decay rate. So what we're doing now is we're going to go ahead and take a look at this problem again. And we're going to go ahead and evaluate that numerator. All right, numerator is going to be, let's see, v is 0, 2 plus s plus 12 times 0.1, all over s plus 6 squared plus 8 squared. X of s is equal to that, is equal to, let's see, 0.1 s plus 112 times 0.1 is going to be 1.2, so that'll be plus 3.2, all over s plus 6 squared plus 8 squared. So, do we know whether it's going to be a sine or cosine? Not a clue. Probably, in the overwhelming majority of cases, probably it will be some of each. Although I think I might have been funny on this one and said, no, but let's see some of each. Okay, so how we do this is we go 0.1 s plus 3.2, it's 0.1, over s plus 6 squared plus 8 squared is equal to, once again we said, if this is going to be a sine of 8t, let's do the Laplace of sine of 8t, e to the minus 6t. So that means it's a times omega, which is 8, over s plus 6 squared plus 8 squared. This is a times the Laplace of e to the minus 6t sine of 8t. We cast it in the form that we know it's going to end up as. Plus b hat times s plus 6 over s plus 6 squared plus 8 squared. Again, this is the Laplace transform of e to the minus 6t cosine of 8t. Okay, and since we know it's going to be in that form, or we know that that's the nature of the answer, we'll put it in that form here and then solve out using these these equations. Now what you notice is that we have a common denominator on both sides. Let's multiply both sides by that common denominator. If we do that, the common denominator actually goes away. So boom, boom, and boom. There we go. If you didn't catch that written down, I guess you get pause, rewind, and do it again. Just kidding. Talking to yourself in a room will do that to you. What do we have? 0.1 s plus 3.2 is equal to 8a plus 6b hat plus b hat times s. Fairly obviously, b hat is equal to 0.1, and then 3.2 is equal to 8a plus 6 times b hat, which is 0.1. So 8a is equal to 3.2 minus 0.6 is equal to 2.6. So a is equal to 2.6 over 8, well, that doesn't look terribly friendly, is equal to, let's multiply top and bottom by 5. 5 times 2 is 10, 5 times 0.6, so that's going to be 13 over 40. All right, so if b hat is equal to 0.1 and a is equal to 13/40, then x of t is equal to e to the minus 6t times 13/40 sine of 8t plus 0.1 cosine of 8t. All right, how did I do? That's not encouraging. What do you know? I got it right. Anytime I get this 13/40, I get kind of nervous, but it's a weird looking fraction. All right, so that's problem 2a. Got 2a down. All right, let's go ahead and do the same thing for 3a. If you got any questions, I guess record it or hit rewind and do it again. So let's see, m is equal to, this time, 2 kilograms. This is 3a. K is equal to 30 newtons per meter. And B is equal to 16. Boy, increasing the damping a little and dropping the stiffness by a lot. I bet you that's going to be overdamped. X of S, same thing. We've still got that going on. Now, is this now going to have a denominator s squared plus b over m, s plus k over m? Yes. But what is b over m and what is k over m? Those are going to be a little bit different form, because now we need to take into account the fact that m is not equal to 1. It's always convenient to have the mass equal to 1, but that's not going to happen. Certainly not on your test, it shouldn't happen. I'm trying to test you on these things to make sure that you're paying attention. So let's write it over here. This is actually going to be equal to 2 plus s plus b over m. 16 divided by 2 is going to be 8. That's going to be times 0.1 all over s squared plus 8s plus 30 divided by 2 is 15, and what do you know? 15 happens to be 5 times 3, which 5 plus 3 is equal to 8. So this is actually equal to 0.1 times 8 is going to be 0.8, so we have 2.8 plus 0.1 s all over s plus 3 times s plus 5. And yes, when you're out in the real world, everything comes out in nice round integer numbers and things like that. Right. Okay, so what that tells us, again, is that x of t then will be equal to a e to the minus 3t plus b hat e to the minus 5t. So how do we figure that part out? What we do is we say 2.8 plus 0.1 s all over s plus 3 times s plus 5 is equal to a over the Laplace of e to the minus 3t, so that's going to be s plus 3 plus b hat over s plus 5. That really didn't look like a b. That's a little better. Now, to get a, listen carefully, write it down yourselves. I'm not going to do this. I'm not going to bother writing it down. To get a, we multiply both sides by s plus 3, and we let s go to negative 3. That will eliminate this term because when we multiply by s plus 3, we let s go to negative 3. That's essentially multiplying that by 0. Over here, we cancel out. And so in other words, a is actually equal to 2.8 plus 0.1 s over s plus 5, evaluated at s is equal to minus 3. Likewise, b hat is going to be equal to 2.8 plus 0.1 s over, instead of s plus 5, now we multiply both sides by s plus 5, and we let s go to negative 5, so s plus 5 evaluated at s is equal to, s plus 3. S is equal to minus 5. That's a minus 5. That's an s. That's a minus 5. So, what do we have here? Let's see. We have 2.8 plus 0.1 times negative 3. But 1 times negative 3 is going to be negative 0.3. So, this is going to be equal to 2.5 divided by minus 3 plus 5 is going to be equal to 2, is equal to 5 halves, otherwise known as, no, it's not, 5 fourths, otherwise known as 1.25, and b is going to be equal to 0.1 times negative 5 is going to give us negative 0.5. We add that to 2.8, we'll end up with 2.3 over minus 5 plus 3 is going to give us minus 2. No good way around that one, is there? Well, heck yeah, there is. Is equal to minus 1.15. All right, we can do it as fractions. We can multiply top and bottom by, I guess, 10. We get 23 over 20. I don't even want to look at it. So x of t then is going to actually be equal to 1.25 e to the minus 3t minus 1.15 e to the minus 5t. That is problem 3a. Ha! Never did give you answers for that. My bad. Sorry. But that should be the answer for that one. I hope. I'll have to go ahead and check myself. I'm going to write that one down here. 3a, 1.25 e to the minus 3t minus 1.15 e to the minus 5t. And we want to do 4a next. So, I've got the answers. I worked them out on MATLAB. I just haven't recorded them. All right. I'd ask you if there are any questions, but I guess it's kind of pointless, huh? 4a. This is Gonzo. And of course, 4a, we've done 2 overdamped. We've done 1 underdamped. Naturally, this one should be underdamped. None of this stuff was relevant to our last problem. The underdamped problems tend to be 2-board problems, whereas the overdamped tend to be single-board problems. So let's see. That's Gonzo. That's Gonzo. And m is still equal to 2. K is equal to 40, and B is equal to 8. So stiffness went up. Damping went down. And so what do we have? Let's see. V naught, yes. S plus B over M. 8 divided by 2 is going to be 4. X naught, 0.1. Denominator is going to be S squared plus 4S plus 40 divided by 2 is equal to 20. And I think you'll see that the factors of 20 being 1 and 20, 2 and 10, 4 and 5, none of them are going to actually add up to give you 4. 4 plus 5 being 9, 1 and 10, or 2 and 10 being 12, so on and so forth. So let's go ahead and figure out what the roots are. S squared plus 4S plus 20 is equal to 0. implies that s is equal to minus 4 plus or minus the square root of 4 squared minus 4 times 20 all over 2, like that, because the coefficient is a. 16 minus 80, what do you know, 64. So that's going to be minus 2 plus or minus square root of 64 all over 2, right? 16 minus 80 gives us negative 64. Also divided by 2 is going to be equal to minus 2 plus or minus j. 64, square root of that is going to be 8, divided by 2 is 4. So plus or minus 4j, j4, however you want to look at it. So that tells us definitely we need to complete the square. We have s plus little a squared plus omega squared is equal to s squared plus 2as plus a squared plus omega squared. The 2a is going to be equal to 4, so a is equal to 2. A squared plus omega squared is equal to 20. A squared plus omega squared is equal to 20. So omega squared is equal to 20 minus 2 squared is equal to 16. Therefore, omega is equal to 4. What do you know? What an amazing coincidence. A, omega. So really the roots are going to be equal to minus a plus or minus j omega. That's the way that it works. What that tells us then, being that we've got these complex roots, being that we can complete the square, then we know that x of t is going to be of the form, well, no, we're right up on the next board. X of t is going to be equal to e to the negative a, so that would be minus 2t. A sine of omega. Omega is 4, so that would be sine of 4t plus b hat cosine of 4t. That will be the form of the answer. I get that out of the form of the roots of this denominator. Now, does that mean that it's necessarily a non-zero and b hat non-zero? Well, of course not. There are certain initial conditions we could choose that will drive one or the other to 0, possibly. But I don't know the answer on this one. We'll have to find out. Anyways, let's go ahead and solve this out then. Going back to the S domain, back to the Laplace domain, what that says is that this x of s right here, we've got x of s right here, okay? We can go ahead and group the terms together. We have 2 plus 4 times 0.1, so let's see. X of s is equal to 2.4 plus 0.1 s divided by, let's check that again, 2 plus 0.4, 2.4, 0.1 s. Got that? Divided by, okay, instead of doing s squared plus 4s plus 20, now let's do it anyways. S squared plus 4s plus 20, because I've got a point I'm trying to make to you, is going to be equal to a. Here's e to the minus 2t sine of 4t. That means that the Laplace of that is going to be a times 4 over s plus 2 squared plus 4 squared. And, oops, not equals, plus b hat times Laplace of e to the minus 2t cosine of 4t is going to give us s plus 2 over s plus 2 squared plus 4 squared. If you don't appreciate where those Laplace transforms come from, check the back of the textbook or any table of Laplace transforms that you find online. They should have the Laplace transform of a damped harmonic function, damped sine, damped cosine, or maybe even both. Now, as you look at this, the point that I was trying to make here is there a common denominator on both sides? And the answer is yeah. This is this. This denominator is this. It's because we completed the square, we made it look like this, but they're the same thing. S squared, 4s, 2 squared plus 4 squared, meaning 4 plus 16, meaning 20. So in other words, I can actually cancel out the denominators on both sides. I won't have x of s at that point, so I'm not going to erase it here and say x of s is equal to that. What I can say is that 2.4 plus 0.1 s is equal to 4a plus 2b hat plus b hat times s. Like that. All right, so once again, pretty obviously, b hat is equal to 0.1, and 2.4 is equal to 4a, oops, got my a and my plus transposed, 4a plus 2b hat is equal to 4a plus 0.2, so 2.2, subtracting 0.2 from both sides, 2.2 is equal to 4a, therefore a is equal to 2.2 over 4 is equal to, let's multiply top and bottom by 5. 5 times 2 is 10, that means equals 11 over 20. A rather odd number there. So here we go, we got b hat there, we got a there, and so we have our final answer for 4a, that x of t is equal to e to the minus 2t, that's where that s plus 2 comes into play, e to the minus 2t times 11 over 20 sine of 4t, right, because 4 is omega, plus 0.1 cosine of 4t. And that's it. We're done. So that's problem 4a. Going to write that one down. E to the minus 2t times 11 over 20 sine of 4t plus 0.1 cosine of 4t. All right. So, moving on, because how much time have I got going so far? Oh, 36 minutes. Crud, I've only got like 24 minutes to go. Like I said, if somebody else wants to use this room and be the gracious person that I'm trying to be, I'll have to let them have it, I guess. Bummer. Let's do 1B, 1C, and 1D. Okay, so 1B, M is equal to 1 kilogram, K, as I recall, was 100, and B was equal to 25. You know, the rate I'm ripping along here, I don't even know if you have to turn your YouTube or your play speed up to 1.5 or not. That's what I usually do with YouTube videos. I get really so bored hearing people talk that I just go ahead and buzz 1.5 and then slow it down when I come to the points that I'm interested in. I really don't know that I want to hear what I sound like when you put me on 1.5 speed or 2. Probably not even coherent. All right. So now we're going to look at, and I'm going to kind of morph these things into the same problem because, well, no, 1B, C, D. How about that? Because they all require the transfer function, okay? Differential equation, x double dot plus b over m x dot plus k over m x is equal to 1 over m f of t. If we take Laplace of both sides to get the transfer function, what do we have? S squared plus, all right, let's even do it this way. S squared x of s minus sx of 0 minus v of 0 plus b over m s x of s minus x of 0 plus k over m x of s is equal to 1 over m f of s. Now, to get the transfer function, I'm going to actually assume that the initial conditions are 0. Maybe I won't do that at first, but I'm going to. Let's go ahead and do that for a second. Solving out for x of s, I end up with x of s is equal to, and I'm going to let you go ahead and do the algebra, the intermediate algebra for yourselves. S squared plus b over m s plus k over m. This is, again, the benefits of the pause button. Go ahead and do that. That's times f of s. And then we have everything else on the other side. We have s plus b over m x of 0 plus b of 0 divided by s squared plus b over m s plus k over m. Now, taking a look at it, this part is going to be the response due to the fact that we've got some f of s. This part will be due to our initial conditions. All right? The transfer function is the function in the S domain that transfers an input to an output. So this is the answer to problem 1b, except that I've got to use the specific values of b and k and m. This stuff is actually not used for any additional problems here, because when you look at 1c, it says use the transfer function developed in 1b to determine the response to a step input with a magnitude of 50, we'll get there, assuming 0 initial conditions. So we're going to assume 0 initial conditions at that point. We also have got problem 1d where we say, okay, f of t is equal to 30 sine of 10t. What's the system's steady state response? Well, the steady state response, these two, the response to the initial conditions, that's going to all go away. Okay, we have either a damped first order systems, like in this case it was what? I forget, 25 s plus 5 times s plus 20, so that meant that this was composed of two terms. There was an a e to the minus 5t plus a b hat e to the minus 20t. Both of those go away at steady state. They're irrelevant. In the case of the damped exponentials, where we damped harmonics, where we had the smaller amount of damping there, we still had an exponential decaying function in front of the a sine of omega t plus b hat cosine of omega t. And again, that exponentially damped function, it goes away. So we can actually ignore this at this point, okay, and actually solve out and just say, look, the transfer function is the ratio x of s over f of s is equal to this. Okay, that is the transfer function. In this specific case, it's actually going to be equal to 1 over 1 is 1, divided by s squared plus b over m being 25, s plus 100, like that. That's x of s over f of s. We can call that h of s if you want to. And so that is the answer to part 1b. Part 1c says, okay, you go ahead and use this transfer function and tell me what the response is to f of t. That looks like this. We go along at time t is equal to 0, we go up to here. That has a magnitude of 50. This is t is equal to 0 right there. If this is f of t, that says that f of s is equal to 50 over s. And we know actually if this is h of s, okay, this is h of s, then x of s is equal to h of s times f of s. You're actually not supposed to use that notation in some senses. That's called convolution, but we'll use it as times, okay? There. And so in other words, for us, for this particular problem, x of s is going to be equal to 1 over s squared plus 25s plus 100 times 50 over s. Let me pause and answer the phone. All right, are we recording again? Yes, we're recording again. It's one of those days. Phone calls, phone calls, phone calls. All right, so the point here is we can actually go ahead and split this up. Then this is going to be equal to 50 divided by s times s plus 5 times s plus 20. And so in our case now, this is going to be equal to a over s plus b hat over s plus 5 plus c over s plus 20. And we solve this out the same way as we did before. Multiply both sides by, for example, s. Let s go to 0, we'll get a. So again, a is going to be equal to 50 over s plus 5 times s plus 20 at s is equal to 0. Now, again, I'm not drawing it out. I'm taking liberty that you can hit pause, rewind, play, pause, all that fun stuff. What I did is I took this, I multiplied both sides by s, this whole term up here, because that is equal to that. So I multiplied x of s by s, which means I multiplied everything in here by s. and then I let s go to 0. S over s canceled out there, so we're left with a. S over s plus 5, let s go to 0, this goes to 0. S over s plus 20, that goes to 0. So we get 0, 0, and a. So that's why we end up with a. Up there, we multiply by s, that cancels out there, we have 50 over basically 100. Okay, because if we let s go to 0 here, then this is actually equal to 50 over 5 times 20 is 100, is equal to 1/2. All right? Similarly, b is equal to, same function, 50 over, but now this time we're going to multiply both sides by s plus 5, okay, to isolate the b. Then we have a b hat coefficient, that's b hat, sorry, is equal to, when we multiply that by s plus 5, cancel those out, we have s times s plus 20, all evaluated at s is equal to minus 5. Has to hold at any possible value of s, may as well pick minus 5. So what we have there is 50 over minus 5 times 15 is equal to 50 over 60, let's see, minus, no, 75, my bad. 5 times 15 is 75 is equal to minus 2/3, like that. That's b hat. C is going to be equal to, you guessed it, 50 over s times s plus 5, evaluated at s is equal to minus 20, is equal to 50 over minus 20 times minus 15. I can do it 50 over 300, I guess, right? Because this is going to cancel out with that. 20 times 15 is going to be 300, also known as 1/6, right? 50 over 300 is equal to 1/6, like that. So my final answer for part 1b is going to be x of t is equal to 1/2 minus 2/3 e to the minus 2t, no, e to the minus 5t, my mistake, plus 1/6 e to the minus 20t. How did I do? Woohoo, I got it right. You never know. Algebra gets us all, right? That's the answer to 1b. Next problem, 1c. Go back to the transfer function and go back to the notes. Actually, if you go through the notes, okay, we said, h of s is equal to 1 divided by s squared plus 25 s plus 100. And so, at steady state for this system, x steady state of t, let's see, for f of t is equal to a sine of omega t. We're going to go ahead and draw that. Then x steady state of t is actually going to be equal to the magnitude of h of j omega. That's the same omega here as we have there. Sine of omega t plus the angle of h of j omega. Same omega there. So we need to evaluate h of j omega, then the magnitude of h of j omega. We also need to evaluate the angle of h of j omega. Pretty straightforward stuff, actually, when you come around to it. I'm going to go ahead and save myself the effort of redrawing this. All right, I'll erase a lot of it, but not everything. H of s is equal to this. Therefore, h of j omega is equal to 1 over. If you plug j omega in for s, you square it, you have a negative omega squared. So it's 100 minus omega squared, that's your real part, plus j, 25 times j omega, so it's j times 25 omega. All right? So the magnitude h of j omega is equal to the magnitude of the numerator, which is magnitude of 1, which is 1, of course, over 100 minus omega squared plus the, that's the real part squared, plus 25 omega squared, and the square root of all that. All right? Similarly, let's go ahead and do this. H of j, now what was the frequency on this? 10. Magnitude of h of j 10 then is equal to 1 over, this is kind of cute, 100 minus 10 squared is going to be 0. 25 times 10 is going to be 250. It's actually the square root of 250 squared is equal to 1 over 250. That was kind of convenient the way that worked out now. The angle of h of j omega is going to be the angle of 1, the angle of the numerator minus the angle of, and this is the tricky part, 100 minus omega squared plus 25, let's do j times 25 omega. Like that. Okay, so the angle of 1 is equal to 0 degrees minus, and then the angle of any complex number is going to be the inverse tangent of the imaginary part, not including j, divided by the real part. So it's going to be minus the inverse tangent of 25 omega divided by 100 minus omega squared. All right, so the angle h of j 10 is going to be equal to, the denominator goes to some interesting thing. So this is equal to 0 degrees minus the inverse tangent of 250 over 0. I recommend you don't try to plug that into your calculator or MATLAB. Well, you can do ATAN too in MATLAB. You can do that. But we also should just go ahead and look at that. What is this inverse tangent? If we have the real part being 250 and the real part being 0, the imaginary part being 250, that's 90 degrees. Now we have negative, so this is actually equal to minus 90 degrees, like that. And so that's at this particular frequency. So what we have then is that x steady state of t is going to be equal to 1 over 250 sine of 10t minus 90 degrees. How'd I do? Woohoo! Oh man. I know why I blew it. Dang it. I told you I never get 100 on my own tests. What did I screw up? X steady state is not just this. If this is a times sine of omega t, you have to put an a in there. Learn from my mistakes, okay? All right, so I've got a. A was equal to 30, I believe. F of t is equal to 30 sine of 10t. So I got to put in the steady state is equal to 30 over 250. The zeros are going to cancel out. That's 3/25. And now I got the right answer. I'm so sorry. All right, so that is part 1D. All right. Let's move on to 2, B, C, and D. Let me see how much time I've got left. How long has this video been going anyways? Son of a gun, 53 minutes. All right. I'm kind of sitting the fan. Okay. Don't have to pick up the kids. Yay! Well, I like picking up my kids, believe me, but kind of hard to teach class and pick up kids when they're doing it at the same time. I'm going to leave parts of this alone. I think that one was probably the same thing too. I might have not wanted to erase that, but we'll see. This is not legit anymore. Second problem, 2, we have stiffness and mass being the same and damping being 12. Alright, so the transfer function becomes same numerator, 1 over 1, s squared plus 12s plus 100 over 1. Okay, so that is part 2b, or not to be. No, it's 2b. So now, I'll come back to the frequency response in a minute here. All right. of this junk. All right, probably only have time to finish up this one and then call it done for the video. F of t is equal to 50 over s. Sorry, f of t is equal to a step of 50 newtons. Therefore, f of s is equal to 50 over s. We double check and see. Yep, step input with a magnitude of 50, assuming zero initial conditions. So, may as well write it up here again. X of s is going to be equal to 50 over s times s squared plus 12s plus 100. All right. Now this one's a little trickier. Honestly, it is. We know the coefficients to this. We know that we had to complete the square. Let's see, that was going to be s squared plus 2as plus a squared plus omega squared, right? And so a was equal to 6, 36 plus omega was equal to 8, okay? Geez, I hope I got that right. Let's see. Yep, I do. Okay, good. So x of s now is going to be equal to a over s, that's for the s term, and then we're going to have a damped sine and a damped cosine term. So I'll do the damped sine first, b hat times 8 over s plus 6 squared plus 8 squared plus c times s plus 6 over s plus 6 squared plus 8 squared. All right, so I've got a damped sine, a damped cosine, and a step. That's the nature of the response to this step input. We know that from looking at this completing the square. We know it from looking at the nature of these roots being complex roots, being minus 6 plus or minus 8j. To solve this out, the easiest way is we can multiply both sides by the entire common denominator. Is that the best way to do it? Yeah, pretty much that's the best way to do it. So what we have is if we multiply this, so I'm going to erase that for a second, and this function is equal to this. Multiply this by s times s squared plus 12s plus 100, okay? And it's the same as all this times s squared plus 12s plus 100. And what do we get? Well, the s cancels out with the s there, so this is equal to a times s squared plus 12s plus 100 plus, okay, the s plus 6 squared plus 8 squared cancels that because this is completing the square of that. And so we have 8b hat times s plus c times s plus 6 times s. That little s didn't work out so hot. Okay. So now what we can do is this is all equal to, and by the way here, that and that cancel out, it's all equal to 50. So we can say it's equal to 0s squared plus 0s plus 50. All right. What do we see here? cs squared, 6cs, 8b hat s. So neither one of those two are going to be equal to the 50. We have 100a is equal to 50. Therefore, a is equal to 1/2. No surprise on that, actually. It's the same answer as before. That's because when you put a step input, it's just the stiffness divided by displacement. That's the final answer on that. Anyways, what else do we have? Let's do our s's now. Let's do our s squares. A times s squared. So a times s squared. There's no s squared here, but there's a c squared there. A plus c is equal to 0. Now I guess we can say s squared is equal to 0s squared. Those cancel out. A plus c is equal to 0. C is equal to minus a is equal to minus 1/2. We got that, we got that. The 8b hat is a little bit, it's the hardest one to get. We have 12a plus 8b hat plus 6c is equal to 0. Where'd that come from? 12a times s, 8b times s, 6c times s. So we can multiply this all, that's the s term, this times s, but of course those cancel out. Now we have 12 times a half makes 6 plus 8b hat plus 6 times a negative 1/2, so that's going to be minus 3 is equal to 0. B hat is equal to 6 minus 3 is going to be 3. Swing sides, that's going to be minus 3/8. And so our answer is going to be x of t is equal to 1/2 plus e to the minus 6t times minus 3/8 sine of 8t. I guess I could do a minus on that, right? And that's going to make that a plus. Plus 1/2 cosine of 8t. Let's see if I got that right. Cool beans, we got it right. Okay, we're almost there. Somebody wants to use this room, so f of t is equal to, and just kind of keep burning on this thing, 30 sine of 10t. Once again, so what we have now is that transfer function almost done. This is a special case. We're actually driving it at the natural frequency, which is why we're ending up with 90 degrees of phase. But h of j omega is going to be equal to 1 over 100 minus omega squared plus 12 j times 12 omega. And so h of j10 is going to be, well, let's not do that. Let's not do it that way. Magnitude h of j omega is going to be equal to 1 over the square root of 100 minus omega squared plus, again, don't square the j, okay? It's plus the imaginary part. The imaginary part is 12 times omega, 12 omega squared, and so magnitude h of j10 is going to be equal to 1 over, it does happen to be 100 minus omega squared goes to 0, so now we have the square root of 12 times omega being 12 times 10 squared is equal to the square root of the squared term goes away, 1 over 120. The angle h of j omega is going to be equal to the angle of 1, that's the numerator, minus the angle of 100 minus omega squared plus j12 omega. Like that. Is equal to 0 degrees minus the inverse tangent of the imaginary part, which is 12 omega, divided by the real part, which is 100 minus omega squared. Like that. So the angle h of j10 is going to be equal to minus inverse tangent of 120 over 0. Once again, going into our complex plane, 120 up here, 0 there. That gives us 90 degrees. So it's actually equal to minus 90 degrees. So let's see if I get it right this time. X steady state of t is going to be equal to 30. That's the amplitude that we drove it with right there. 30 times the magnitude h of j omega. So times 1 over 120 sine of 10t minus 90 degrees is equal to 30 over that's 1/4, right? 1/4 sine of 10t minus 90 degrees. Oh, how'd I do? Ta-da! Got it right. Okay, that's enough of a video. That's solving the first two problems. The second two problems you can do similarly. I'll come up with some answers for those and let you check them. See you soon, actually, although you'll probably not see this for a while.